All right, so I'm going to give you guys a couple definitions first so that we can continue our conversation. Last time I talked about the RAA axis, the renin-angiotensin-aldosterone axis, and then we talked about renal threshold. I gave some definitions at the end: renal threshold, transport maximum. And just as you guys were running out the door, I think I gave you natriuresis, the term natriuresis, which is the elimination of salt from the body. So I have a couple more definitions so that we can have a more sophisticated conversation. Just the words micturition, first of all. Micturition is essentially urination. It's another word for urination. It's the elimination of urine from the urinary bladder. On the other hand, the word diuresis is the elimination of systemic fluid. All right, micturition is a process of the urinary bladder. Diuresis is a renal process, a process whereby the kidneys are going to pull fluid out of the body and produce urine. It also has the implication that there's going to be a large volume of urine that is produced. A diuretic is simply a chemical that's going to promote diuresis. And there are a number of different ways you can achieve this. So diuretic therapy is going to reduce the blood volume and thereby the blood pressure. And as that happens, it's going to pull the water is going to come out of the extracellular space into the plasma to replace the fluid that's being drawn off of that. So it'll also reduce extracellular fluid volume. There's a number of reasons to put people on diuretics. Often it's because people have high blood pressure, or I don't know. There's a host of reasons. Maybe you have edema for some reason. Systemic edema, maybe. I don't know. Anyways, but here are, I'm just putting a couple diuretics up there to show you that there is several different categories, both chemical structural categories and functional categories of diuretics. They can attack different places in the nephron. So the first two up there are both loop diuretics, and they have pretty different. So an example of targeting the same place in the kidney, but having different chemical, pretty widely different chemical structures. They look pretty different to me. And then there can be. So here's spironolactone. This is an aldosterone agonist. And you'll remember that aldosterone is produced by the renal cortex from steroid precursors, and it looks kind of like cholesterol, which most of the steroid hormones are made out of. So, and that's going to attack a different part of the nephron. Specifically, aldosterone functions along the distal convoluted tubule and the collecting ducts, as we saw last time. All right, so I'm just, again, going to slowly build up the story here. With this whole idea of water balance, the idea is simply that the water that is consumed has to equal the water that's lost in the body. We need to maintain appropriate water balance. If you don't consume as much water as is being lost, that's a problem, of course. So I kind of made this little schematic flow here that shows both the regulated and unregulated aspects of water balance. So there is an amount of unregulated water that leaves the body, right, that we don't really have control over. There is an amount of fluid that leaves the body into the feces. Feces is not desiccated, right? There is water that is in that. And then we also lose a significant amount of water through our breath and through the skin. Has anybody ever read the book Dune? Is any sci-fi, old school sci-fi fans in here? Well, yeah, Dune, right. So, in Dune, they live on this desert planet called Arrakis, and they have to wear these so-called still suits, these suits that collect all of the fluid that is lost in perspiration and through their breath, so they can into these pockets on their body, and they drink that water to try to reclaim some of it. Anyways, there is a significant amount of water, about a liter a day, is lost via these unregulated mechanisms. And because of that, we have to have tight control over both what water comes in and what other water can leave the body. So the regulation of water in is mostly through these behavioral mechanisms. And you've already seen a little bit of that, the effects of angiotensin on the brain, on the hypothalamus. So this gives rise to our thirst and our desire for salt. And then the other half of this on the conservation side is at the kidneys, and so the reabsorption of water from the tubular fluid. And the goal here is to simply conserve water by producing urine that is concentrated relative to the plasma. If the urine that you're eliminating is a higher osmolarity than the plasma, then that is a net conservation of fluid, right? Or you can eliminate water by simply the opposite, making urine that is more dilute relative to the plasma. All right. So, and then I put this thing together because it's kind of hard to think about all of the moving parts, I think. So when we talk about water balance, you can't talk about water balance without talking about the regulation of sodium and the other osmolytes. But sodium's the big one. There's so much sodium in your serum that it kind of swamps out the effects of all the other cations. So it's really about water and sodium. And let's look at these different cases of circumstances that the body physiological circumstances, kind of simple cases that the body may find itself in, and the effect on the blood volume and the blood osmolarity. Blood volume, of course, being the regulation of water, and osmolarity, as I've just indicated, the regulation of sodium. So say we're dehydrated. You become dehydrated. You're going for a jog or whatever, and you have a lot of unregulated water loss through the skin, through the breath, etc. This is going to decrease the blood volume. This will decrease the blood volume, but the blood will relatively have a higher osmolarity. Right? It's going to go up in concentration of salt. And if that is the case, you will see down here in the bottom the response hormones. Antidiuretic hormone is going to be an important response hormone, because antidiuretic hormone will help us reserve water, but go through natriuresis. All right, so it'll inhibit diuresis but promote natriuresis. To remind yourself of that, I'll show some slides in a moment, but you can refer back to the diagrams that I showed last time to see that. Or maybe we have blood loss for some reason, an injury or whatever. If that's the case, our blood volume will go down, but we are also losing osmolytes in that. It's not just water that's coming out of us, it's the salts that are going out of us. So we're going to have a different response. This is really why there's these two axes, the RAA axis and the HPA axis, that work in tandem, sometimes in concert, sometimes in contrast to one another, depending upon what the needs are. Or maybe for some reason you eat a lot of salt. You go see, what is that, Isle of Dogs this weekend, opening at the Railroad Square, and you get yourself a giant bucket of popcorn, and you just start taking that down. And your salt goes way up. So this is you're also thirsty, so you're going to start drinking a bunch of whatever. Hopefully not anything with a lot of sugar in it. But it's going to increase both your blood volume and the osmolarity. It doesn't have to increase the volume, but it certainly will increase the osmolarity. It tends to increase blood volume, though, because water will follow that. Or perhaps instead you are going to go for a walk and drink a... Yes, ma'am. Yeah. So if you have a high osmolarity in the plasma, that's going to increase the gradient that is driving, for example, contracurrent multiplication or diffusion of water out of the collecting duct. Right? It's going to increase that gradient, so you're going to end up retaining more water. And it can also, like eating a bunch of salt can trigger thirst responses, so you'll be more inclined. That's why there's a star next to it. It could be, blood volume could stay flat, but it's likely that it's going to increase. All right, so that's why I kind of, there's a little caveat there. Anticipating someone like you, smart, catching me. Anyways, or you could just drink a bunch of plain water. And not bringing the electrolytes into the body, and that would increase blood volume but decrease osmolarity. So there's going to be different responses, varied responses between the HPA and the RAA axis in any of these certain cases. I think I've wrung everything out of that slide. Okay, so let's look at ADH a little bit in more detail here, antidiuretic hormone. So there are really two ways that the body can stimulate the production of antidiuretic hormone. They can either be, so that's these two boxes here. It can either be stimulated by the arterial baroreceptors. So there are these pressure receptors in the aortic arch and in the carotid bulb. And they are going to detect a decrease in blood pressure, right? And the goal here is for them to maintain proper perfusion. They're monitoring blood pressure because their concern is making sure that we're getting enough blood to the peripheral tissues, right? And if there's a low blood pressure, these arterial baroreceptors are going to respond, and they're going to send signals via the various cranial nerves, cranial nerve 9 and 10. And those will have projections into the hypothalamus and hit these paraventricular, the cells in the paraventricular nucleus. The cells in the paraventricular nucleus are themselves osmoreceptors. So they're paying attention to the other side of this. They're looking for an increase in the osmolarity of the blood. Is there too much salt in the blood? So the baroreceptors are, is there not enough water in the blood? Or the paraventricular nucleus looks at the other side, is there too much salt in the blood? Either way, we'll start this mechanism in the hypothalamus where these cells are neuroendocrine cells, where they are going to produce antidiuretic hormone. And the hormone that is produced in the cells in the hypothalamus comes down, the axonal transport comes down through what's called the infundibulum, this little connection to the little berry hanging off the bottom of your brain called the pituitary, goes down into the posterior hypophysis or pituitary, and goes into this portal system, which is this bed of capillaries that you see right there. ADH gets released into the blood at the hypophysis, at the pituitary. Blood comes in and then carries the ADH throughout the body, and ADH is going to have two effects. First of all, it's going to cause the circulatory system to contract. All right, the like blood vessels are going to contract, raising the blood pressure, essentially reducing the effective volume of your circulatory system. Okay, and thus pumping up the blood pressure a little bit. And then, so that's the container that the blood fits in, but we're also going to try to actually pump up the volume of the blood, and that's the effect of ADH on the kidney and the resorption of water. We're going to see exactly how it affects the kidney in a moment. You guys still with me? All right, good. Here we go. So you may see the word vasopressin in the literature or a textbook, or I don't know, someone talks about this again in your life. But antidiuretic hormone is also known as vasopressin. Anyways, the way it works, it has a very direct control. It is a hormone that has a direct control on the expression of a specific protein. That protein is aquaporin. You see a picture of it down there. When ADH is present in the kidney, when it's been triggered and released by the pituitary, it inserts these aquaporins into the membrane of the simple cuboidal epithelial cells of the DCT and the collecting ducts. And this enables water to go down its diffusion gradient, right, and to diffuse into the interstitial tissue of the renal medulla. So with the presence of ADH, that's going to pull water out of the urine and lead to a smaller volume of darker urine. All right, smaller volume, darker urine. And then if there is no ADH present, there's not going to be significant water resorption at the DCT or the collecting ducts, because we're not getting the signal to put the channels for the water to come out of the urine into those cells, right? The aquaporin is not going to be expressed without the signal from antidiuretic hormone, all right? So you'll have a larger volume of more dilute urine, okay? So this is the mechanism that ADH works by. Any questions? Yes, ma'am.
Does ADH control expression of the aquaporins, or does it control just like activation?
That's a great question. I believe it is direct expression. I think it triggers a signaling cascade that maybe has multiple forks on it, and you're catching me in not knowing those pathways completely, but I believe it is an expression of aquaporins and not just it's not just fusion with the membrane and expression of them. I think it's actually production of aquaporins. It's like a transcription factor. All right, good question. All right, so we talked about how to turn ADH on. Let's talk about how to turn it off. Inhibition. So there's a couple ways, and I'm not going to talk about BNH, or also known as BMP, but I am going to talk a little bit about ANH, and the mechanisms are the same. This was on the list of minor molecular factors that I put up there, but it is important. Turning off the system, turning off ADH is important. So there are stretch receptors, this time in the atria, that are sensitive to a larger than normal blood volume. And if that's the case, they make this atrial natriuretic hormone, ANH, also called atrial natriuretic peptide. Sometimes you'll see AMP. There's a third acronym. I forgot what it stands for. Anyways, the effect of there's multiple effects of this ANH, and it has a direct effect on the hypothalamus and the pituitary. So it's going to stop ADH secretion. It's going to downregulate the paraventricular nucleus, the cells in the paraventricular nucleus of the hypothalamus. It's also going to promote vasodilation, all right, in opposition to ADH. So it's kind of like has an opposite effect on the circulatory system. And then again, in the kidney, it has a series of effects. It's going to promote natriuresis, so the elimination of salt. It's going to promote diuresis, which is the elimination of fluid. So it wants to get rid of the salt, because remember, water follows the salt. Water is going to follow salt in general. And then it wants to get rid of water, so it's going to have directly promote diuresis through a couple mechanisms, but one of them is through the inhibition of ADH, antidiuretic hormone. So we're not going to be putting aquaporins in there. And then it also turns the RAA axis off. It inhibits renin. So ANH has a complex suite of effects on the kidney. The goal of all of it, though, is that the body simply wants to rid itself of excess fluid volume. Too much fluid is arriving at the atrium. The atrium, you can kind of think about the atrium on the right side of the heart as like the brain of the heart. That's where the SA node, the AV node, both of them exist. And it has these stretch receptors. And so it's integrating information about heart rate and cardiac output, right, with blood volume that's arriving in the heart. Like, is the preload on the heart too high given the demand on the heart, right? Like, is the heart, you want high preload if you're running away from what I said, werewolf senators or something like that. But if you're not, you're just sitting there and you have high preload with a low heart rate, then the stretch receptors in the atrium are going to say, the blood volume's a little high, or blood pressure's a little high right now, so maybe it's time to lose some fluid. You guys with this? Lots of moving parts. All right, so here's a little recap. Water, sodium, and potassium gets into the blood through the GI tract and is in exchange with the intracellular space. I didn't talk about, and I won't really talk about insulin or the catecholamines very much. The catecholamines like epinephrine and norepinephrine and all those things that your suprarenal gland makes. But their job is to control that process of exchange with the intracellular space in the blood. Like, they have their direct target is peripheral tissue. And then there's the rest of it, is the kidney here. So, and we can think about sodium, potassium, and water export into the, or resorption into the blood. And they're going to be controlled, positively affected by aldosterone, also cortisol, and angiotensin and ADH, and negatively affected by, so this chart has it as ANP and BNP. That's ANH that I just talked about, the atrial natriuretic hormone. BNP is the brain natriuretic peptide or hormone. And it has the same functions as ANP, except the sensors are in the brain rather than the atrium. And then there is excretion of sodium, potassium, and water through filtration into the kidneys, and then elimination through the urine. So this is sort of a little bit of an overview that is recapping what we've done so far. Because I'm about to dive into the HPA axis a little bit more. We've been dancing around it, but I'm going to show you the HPA axis in conjunction with the RAA axis. All right. So this slide here gets a little wild, but we're going to walk through it nice and slow. All right. These are all the players, right? We've got heart, lungs, liver, kidneys are the big ones, brain, circulatory system, and this yellow blob is the suprarenal gland. All right, so let's start walking through the hormonal regulation of intravascular volume and blood pressure. These slides were in the original PowerPoint, though, right? You guys have seen this. Is that right? I don't know if anybody's looks at that ahead of time. But okay, so first, let's just review the RAA axis that we talked about. Here's the first part of it. So drop in blood pressure at the glomerulus stimulates the production of renin. Renin is going to cause the conversion of angiotensinogen to angiotensin 1. Angiotensin 1 is going to get converted to angiotensin 2, which is the active form by ACE, the angiotensin converting enzyme that's at the lungs. So this is all pretty established, and we'll get to what angiotensin 2 does in a moment. But let's start out on the HPA axis. So the thing that normally engages the HPA axis is some sort of stress. It can be osmotic or volemic stresses. It can be other stresses, just whatever. Maybe you're running away from a werewolf, or you're trying to learn about this stuff in class. Like, some kind of stress is going to have an effect on the hypothalamus and the pituitary gland. And I've said that the pituitary is sort of the top of the pyramid for the endocrine system. And the way that when we talk about endocrine, you'll see this motif where the way it works there is there's going to be some kind of releasing hormone that causes the release of the actual hormone that is going to affect some effector, some gland, or something in the system, some other tissue in the system. So there's the production of a releasing hormone that's under the control of some sensor that's sensing something. And that releasing hormone causes secondary production of the hormone that's actually going to give us the effect that we want. So stress causes the production of corticotropin-releasing hormone. And the effect of corticotropin-releasing hormone is to release the corticotropin hormone, the adrenocorticotropic hormone. So corticotropin-releasing hormone comes out of the hypothalamus. That's the H in HPA. And then ACTH, adrenocorticotropic hormone, is the P in the HPA. ACTH gets released into the bloodstream, and this is going to be what causes the production of these steroid precursors. So remember when I showed the HPA axis and I put aldosterone on there, and how angiotensin can help potentiate that conversion. I didn't really talk about where these steroid precursors come from, and that's crosstalk with the HPA axis. The HPA axis is the ACTH, adrenocorticotropic hormone, is going to cause the production of these steroid precursors in the suprarenal cortex. All right, so that gives us some cortisol. That's going to have some effects, and the aldosterone. So now let's start getting some actual physiological effects. Angiotensin, let's go back to the RAA axis, is going to have all of these effects at the kidney, specifically at the proximal convoluted tubule. You're going to have an increase in sodium resorption, and there's going to be an increase in carbonate because of angiotensin. Now, on the other side, aldosterone is at the distal convoluted tubules is going to be increasing potassium and hydrogen ion secretion. And this goes back to that diagram that I showed last time. All right. All of this leads to a decrease in the serum potassium and alkalosis. So that's going to make your blood more basic. We're getting rid of hydrogen ion, we're getting rid of acid, and we're making the blood more alkaline. All right. So, and you can also see that angiotensin is, as I had shown in the previous diagram, angiotensin is what's actually causing the production of the aldosterone from the steroid precursors. All right, let's add some more in here. Angiotensin is also leading to vasoconstriction. We talked about that. Anyways, the point of the central box, the control over the osmolarity of the tubular fluid leads overall to the resorption of more water, the retention of more water. As that happens, our blood pressure goes back up because blood pressure going down is what started this whole cascade of dominoes. All right. So we've kind of come full loop. Blood pressure went down, engaged RAA on this side, engaged HPA on the other side, had the physiological effects that lead to an increase in blood pressure. You guys still with me? Lots of arrows appearing here. We're working through it though. All right. So let's add in the part about ADH that we just talked about. The last piece of the puzzle. We're getting close here. So ADH is responsive to an increase in serum osmolarity or the stretch receptors in the aorta and the carotid bulb. And that leads to vasoconstriction and also further water resorption by putting the aquaporins in the DCT and the collecting duct. Again, reinforcing the increase in blood pressure. I think that's all of the positive arrows. Now, I may be wrong here, but the next step, yeah, I'm right. The next step is to just turn it off. We got to turn it off. There's got to be some negative feedback mechanism that's going to turn this whole mess off. Well, if there's an increase in blood pressure, the first thing that happens, it's going to turn off renin. And in so doing, it's going to turn off the whole RAA axis. That whole side of the cascade is going to get downregulated. So increase in blood pressure decreases the production of renin by the juxtaglomerular cells. Next step. And let's add the last little bit that I talked about with ANP and also BNP. So ANP is going to, well, let's bring it from the blood pressure. Blood pressure, increased blood pressure is registered by the atrium, this intracardiac pressure that I talked about with the stretch receptors in the atrium. That starts the production of ANP and BNP. And ANP is going to have the opposite effect on the regulation of all the osmolytes at the kidneys. And it's also going to vasodilate, as I had shown on that previous slide. So I know this looks crazy, but this is the collection of everything we've talked about so far. This is sort of a summary slide of everything. I think there's one last arrow just pointing out that the role of cortisol here is to turn off the HPA axis. As cortisol goes up, it's got a negative feedback loop. So the HPA axis turned on the steroid precursors, which led to aldosterone, but also cortisol. As cortisol, a stress hormone, goes up, it's going to turn off CRH, the corticotropin releasing hormone, and the downstream ACTH. All right. That's a lot of squiggly arrows on one and boxes on one slide, but it does put everything together in one picture for you. I tried to walk through it one at a time so it didn't juggle your brains too hard. Are there questions on this before I move on? There must be. Okay, well, all right. So let's take a deep breath and look at, in fact, let's actually take a deep breath. That's good. All right, let's look at a summary of what's actually happening here. Let's try to look at the nephron once. So we have the filtrate being produced at the glomerulus, and there is the retention of sodium chloride, various nutrients, of course, the glucose, all of these PCT functions like the export of hydrogen ion, the import of carbonate. All of those things, you'll remember from the slide on the PCT I put up, are driven by sodium. Then there's the loop of Henle and countercurrent multiplication, where in the thick ascending loop we have active export of sodium chloride using ATP. That sets up a gradient, a concentration gradient that drives the resorption of water along there. Pardon me. And then finally is the distal convoluted tubule and collecting duct, both of which are under the control of aldosterone. Did I remind you that the PCT was under the control of angiotensin too? Anyways, distal convoluted tubule under the control of aldosterone. And it's differential resorption of water and sodium chloride there. That's kind of an overview. So what is it that we're actually getting rid of? What are the waste products that we find in our urine? So there's going to be two general sources of nitrogenous waste. A lot of what is in the urine as a waste product is just nitrogen-containing compounds. They come from two sources, either proteins, the degradation of proteins, or the degradation of nucleic acids, the catabolism of nucleic acids. So on the protein side, we break proteins into amino acids into ammonia. The liver takes ammonia and makes urea out of it, makes it a little more soluble, turns it into urea. And then on the nucleic acid catabolism, we're going to have nucleic acids get broken down into, whether it's a purine or a pyrimidine, it's going to be turned into either uric acid or creatinine. And creatinine is also produced by creatine phosphate catabolism breakdown, mostly from muscle cells. All right, so these are the players, and I'm not going to talk about most of them, except creatinine I'll talk about a little bit because it's an important blood marker for kidney function. So let's begin to look at, along the top I've stretched out a nephron here in all the different sections of the nephron, and below it I just have a graph, a normalized graph of all of the different waste products that you can find in the urine, or in the tubular fluid, the nascent urine. And you'll notice an important one here is that creatinine is actively excreted into the urine at the PCT. So it's higher than the level that you would normally see based purely upon filtration rate. Whereas water, the level goes significantly down even without ADH, but if ADH is there, the water level goes extremely low. And then the other nutrients you can see as they drop in kind. So the important thing is creatinine. And the point being here that if the creatinine levels in the blood, if you do a blood test and you see abnormally high levels of creatinine, that is diagnostic of renal dysfunction, renal insufficiency of some sort. It's like the primary indicator that your kidneys aren't doing their job. They're not able to excrete the creatinine that is toxic if it accumulates too high in the blood. So this leads me to talk about kidney disease. What kinds of things can go wrong with your kidneys? A number of people had asked for more pathology, so I chucked this in here. High blood pressure, we talked about that already. About 30% of kidney disease comes because of people are not controlling their blood pressure properly. Maybe there's a number of reasons that your blood pressure can be high. A lot of lifestyle reasons, also old age. On the other hand, the majority of kidney disease is actually because of diabetes. It's not even a kidney problem. It's a kidney symptom, right? It's a problem with can either be your pancreas or your insulin insensitivity, peripheral insulin insensitivity, whether it's type 1 or type 2 diabetes. But 44% of kidney disease is because of diabetes. And then there's a bunch of other reasons. Maybe for some reason you drank some ethylene glycol, antifreeze. That would be a bad thing. But there about 7% is glomerular disease, glomerular nephritis, Bright's disease. Bright's disease is definitely easier to say. That we started out on Monday talking about. There's a couple other reasons. Polycystic kidney disease, you can get kidney stones. So what happens when the kidneys go bum? You get hemodialysis. Has anybody had a grandpa or a grandma have to go through this? Not fun. What are they like after they go through that? Have you ever been with your grandparent? Sluggish. They have they basically pump all the blood out of your body a little bit at a time, and they put it back, but they pump it all out and filter it. And it really does take a real toll on these people. It's exhausting and tiring. They're out of it for a day or two. So the blood comes out, goes through this dialysis tubing. They remove the fluid and then put it back. This is how it actually works. People say hemodialysis. Actually, there's two processes here. There's hemodialysis and hemofiltration. Hemofiltration is a convective thing. So the difference between convection and diffusion, actually convection is more like advection, but it's like imagining convection is like the water flowing through a stream, whereas diffusion is if you dropped a packet of dye in the stream and it would slowly diffuse out, but it would also move down. So convection is bulk motion of fluid, and that's driven by the hydrostatic pressure of the blood. So the dialysis tubing is kept at low pressure, and a bulk fluid passes through the dialysis membrane. But there's also a concentration gradient, and that's what. So it's hypotonic in the diffusion dialysate, and solutes pass across that membrane. So only actually about 20% of hemodialysis accounts for the purification of the blood, and about 80% is just hemofiltration by the pressure of your own blood. The other type is peritoneal dialysis. A lot of people do this. I think I talked about this when I talked about the serous membranes. Did I? So there's the peritoneum. It's the serous membrane in the abdomen that you have, and they punch a hole in the abdominal wall and fill the abdominal compartment, not the gastrointestinal tract, but the abdominal compartment with fluid, and stuff passes across it. There's a lot of advantages to this. They live longer, they have more mobility and flexibility, easier to travel, et cetera, et cetera. Disadvantages, you got to do it every day. You don't get a day off. Your grandparent probably had to do it once a week or something like that. Yeah. And the catheter can affect people's body image because they have to have this thing attached to them. So your blood glucose can be kind of difficult to control in diabetes. One of the ways that they keep, so you may imagine in dialysis, how do they like retain glucose, for example? How do you not just pull all the blood sugar out? Well, the solution, it's got enough sugar in that solution so that glucose, its concentration gradient's not going to pull all the glucose out of your blood, but it can really, for a diabetic, it can throw off their blood sugar. And there are a lot of diabetics with kidney disease, as we've talked about. Yeah, what do I got? I got a minute on my phone here. So I get to talk a little bit about diabetes mellitus. Diabetes mellitus, there's type 1 and type 2, juvenile diabetes versus adult onset. Type 1, that's just the pancreas does not work, doesn't produce insulin. These people walk around with a pump usually. And then type 2, this is kind of a more insidious problem. This problem is insulin resistance. Your cells just cannot take up glucose, so you have high level of glucose. This leads to a bunch of problems with peripheral neuropathy. It's like a peripheral vascular disease. And because of that, the kidneys are particularly susceptible, right? Because there's all these superfine capillary structures there that are easily damaged by the conditions of diabetes mellitus. It's a massive problem. This is my last slide. Here, I love this stuff, the epidemiology of it. It costs, so what year is this? This data is almost 10 years old now. $218 billion a year in America. That is a lot of dough, folks. That's a lot of money just dealing with direct problems of diabetes, type 2 diabetes. 25.8 million, probably closer to 30 at this point, between 8 and 10% of the population. That means, I'd like to think that we're all healthy in this room, but that means, just statistically, if it was a random sampling, that there would be a number of you in the class that have it in this country. It's massive. They say that pre-diabetes, 80 million people in the United States, folks. That's over a quarter of the U.S. population. That's like a third of the people in the country. Huge, huge problem. And it's not just our problem. America has exported its diet to the rest of the world. It is an increasing problem throughout the world. What's the take-home message? Well, have a diet like, I don't know, it looks like sub-Saharan Africa is doing the best on the planet there. Maybe Mongolia. Find out what they're doing. All right, so that's all I have to say.